Hello and welcome to this 8th video in our lecture on remote user authentication. In this video, we want to take one step back from just looking at authentication and again look at the way that crypto systems are often used these days. As we talked about, oftentimes a hybrid crypto system is used. So a hybrid system has two steps. In a first step, we use public key cryptography to establish a symmetric key. So a standard example of that is the Diffie-Hellman algorithm, where we use public key cryptography so that at the end of the protocol, the two parties have a shared symmetric key that nobody else can discover. And then in a second step, the parties will use the symmetric key, so they'll use symmetric crypto to encrypt all of their communication. So they're going to use symmetric crypto for confidentiality. So remember, the reason that these hybrid systems are used is because public key crypto is extremely computationally expensive. So you don't want to be encrypting all of your messages using public key crypto. So instead, we just use it for a short time just to establish a short symmetric key, and then we encrypt everything using that symmetric key. So now we want to think about how does authentication fit into this kind of systems. While authentication is something that we do at the beginning of a communication, at the same time or around the same time where we do the establishment of the symmetric key. So the thing we're going to look at now is how we could be combining the authentication protocol with the part of the protocol that establishes the symmetric key. So we're going to try to combine this first step with the authentication protocol. Okay, so the first thing to realize is that when using a symmetric key to enforce confidentiality and sometimes also integrity, as we discussed earlier, so one or the other or both, you don't want to be encrypting a lot of messages with the same key. This is because the more messages are encrypted and intercepted by the attacker with the same key, then the more information the attacker has to try and break the crypto. So you don't want to be using the same key for month and month at a time, because then the attacker can capture, thousands and thousands of messages and has a better chance to figure out what the key was. So keys must be used for a short time. Typically, we say that keys, a symmetric key, should just be used for one session. And such a key is called a session key. So what is a session then? Well, a session is just a relatively short sequence of messages that two people send to each other when communicating. So for example, if you are making a transaction on Amazon, each transaction could be considered a session. So you connect to Amazon, you pick an item, you add it to your cart, you check out. That could be a session. And the next time you go on Amazon, it's a different session. And for each session, you will use a different symmetric key. This is called a session key. That's a key that's only used temporarily during that one session. And keys are chosen randomly, so you don't use the same key twice in two different sessions. So again, the advantage of using a session key is that it gives less information to the attacker to break the crypto. And also, if the key is compromised at some point in time, then the messages that are compromised are only the messages that were sent during that one session, not a much longer sequence of messages. So again, we should be choosing these session keys, like any keys, randomly, so they are not predictable to the attacker. And the thing we want to do now in this video is to look at whether we could combine this first step of a hybrid system. Again, this first step is the step that establishes a session key, and to combine it with the authentication protocol that we've been discussing in this lecture. Since this is done at the beginning of each session, namely you must establish the symmetric key between the two parties, and the parties must authenticate themselves, at least one of them, sometimes both parties. Let's try and discuss protocols that do both at the same time. So here is a proposed protocol that combines the establishment of a session key and the authentication process. So we have two parties, Alice and Bob. Alice is sending her identifier and a random number or nonce to Bob. Bob is going to take this nonce and is going to build, so this is his challenge, is going to build a response. Before he does that, Bob though is going to pick a random key K and is going to concatenate it to the nonce, and then he's going to encrypt it using Alice's public key. It will send the resulting message to Alice. Alice gets a message that was encrypted with her public key, so she can decrypt it with her private key, thereby getting access to both R and K. And because these have a fixed length, she knows how to separate the R from the K. That means Alice now has access and knows the key K. And then what she does is she will use R, maybe add 1 to it, concatenate that back with K, and encrypt the whole thing with Bob's public key and send that to him. And then Bob is able to decrypt this message using his private key and recover K and R plus 1. So the first question to ask is this a secure way to establish a session key? And the second question is, who is securely authenticated in this protocol? Please stop the video, think about the answer to these questions, and come back to discuss some answers. So the first answer is yes. The key has been securely established because Bob is the one that randomly generated it, so he knows it. Alice was able to obtain it, as we just described, and the key point is nobody else should be able to get it because it was sent twice, and in each case it was sent with encrypted with the public key of the parties. So the only person who can decrypt it is the people who know the respective private keys. So that's a good feature of this protocol. Session key establishment appears to be secure. Second question is, who is authenticated? Well, notice that when Bob receives this message, it was encrypted using his public key, so he can decrypt it. But this message must have come from Alice because this message contains the encrypted version of the key as well as the encrypted version of R plus 1. And since Bob sent that message encrypted using Alice's public key, Alice is the only one who could have decrypted that message and then send this message back. So Alice is authenticated to Bob. How about Bob? Is Bob authenticated to Alice? Well, this is the weakness of this protocol. The answer is no. There's nothing in this protocol that proves to Alice that Bob is who he says he is. Notice she sends the nonce, her nonce, and then anybody could have received it and encrypted using Alice's public key. So notice in this case, the nonce that Alice uses is basically useless to authenticate Bob. On the other hand, Bob, that doesn't appear that Bob is sending a different nonce to Alice, but in fact, the key K is serving as Bob's nonce or challenge to Alice. And this is the response from Alice. So in this case, only Alice is authenticated. So Bob is not authenticated. So that's one weakness of this protocol. So before we try to find a better protocol where both parties are authenticated, let's try to achieve the same level of security, at least using a digital signature mechanism instead of an encryption mechanism. So here is a different version of a similar protocol. So in this case, the first message is the same. Alice sends her identifier and a nonce to Bob. Now what Bob does, it will generate a random key concatenated to the challenge that Alice sent him, and then he's going to encrypt the resulting string using his own private key. So therefore, Bob is signing this message. So Alice definitely knows that this message comes from Bob because it was signed with his private key. Then what Alice does is, while she can decrypt this message using Bob's public key, so she's going to get the key. That's the good thing. She's also going to see that the nonce was properly encrypted with Bob. So again, the nonce can be used to prevent replay attacks. And then Alice is going to be able to take the R and the K, get a new message together, and then encrypt it using her own private key, meaning she's going to sign this message, send it to Bob. So Bob is also going to be convinced that Alice is the person on the other end because she was the only one who was able to encrypt the key K. So Alice is also authenticated. So the advantage of this protocol is that both parties are authenticated. So here we have mutual authentication, which is different and better than the previous protocol. However, this protocol has a significant weakness. So make sure you identify it before you listen to the following discussion. So the main weakness, of course, is that the key K, that's supposed to be the session key, is not secure at all. Because notice the key was generated by Bob and then it was signed by Bob, but it was not encrypted. Notice anybody has access to the public key of both Bob and Alice. So anybody could have taken this message, decrypted it using Bob's public key, just like Alice did, and then get access to the key. So the key is definitely not secure, and the establishment part is definitely not working. So in conclusion, we have two different protocols in this video. The previous protocol is able to establish a session key in a secure manner, but only one of the parties was authenticated. Whereas in this protocol, both parties are authenticated to each other, but the protocol does not enable them to share a session key securely. So is it possible to combine the best of both worlds and to come up with a protocol that is both able to share a session key securely and to perform mutual authentication? That will be the topic of the next video.